Welcome back. Glad you tuned in. We are still talking polar to rectangular conversion in terms of these equations, and we're still on page 5 of the polar packet, but you are in luck because we have saved the two spiciest questions for last in 3 and 4 on the middle of this page. So hang on to your double angle identities. We're in for a cool mathematical ride. So let's look at number 3 first. 3 just looks so tame. I stare at it, I see an r squared equals cosine of theta. How bad could that be? And something even pops out at me. The first thing that runs through my head is that I know x squared plus y squared is an easy plug-in for the left-hand side. It's not actually so easy of a plug-in for the right-hand side, though. If this were an r cosine of theta, it would actually be a lot quicker and simpler. Now, I can plug in for cosine of theta, x over r. That's what it equals. It still leaves you with an r in your expression, so you'll still have to take care of that, which you can. But I want to offer a different suggestion. I want to say, for the sake of making the right-hand side substitution so much nicer, I want to do like we did on a previous problem and introduce another factor of r to both sides. So here goes nothing. We're going to write this as r cubed equals r cosine of theta. What it does for us that's awesome is it lets you just plug in an x on the right-hand side. That's beautiful. On the left-hand side, we can handle this too. We've seen in previous questions that if you want to sub in for just r, according to the square-rooted Pythagorean theorem, it's the positive or negative square root of x squared plus y squared. And that's going to be cubed because we had r cubed. So a pat on the back is in order because we successfully got this in terms of x and y, but I still am interested in making it look nicer and doing a little bit of algebra to clean it up. So let's leave no radicals in our solution. A radical here is just like raising something to the 1/2 power. So this is like saying plus or minus x squared plus y squared instead of to the third, because there's a square root, to the 3/2 power. That's an equivalent way to write that expression. Now we're trying to get rid of the fractional power. Let's square both sides. That's thereby multiplying that fraction by 2, and it should cancel the denominator. So if I'm going to try to write this in green. I'm going to square the left side, and I'm going to carefully square the right side. So that gets rid of the plus or minus. It gives you x squared plus y squared cubed. That just looks a lot nicer, just more pleasing to the eye. And on the other side, you have x squared, and that's how it's looking. If I also want to get rid of the parentheses, I could cube root both sides right now too. So now I'm just doing a couple other things to change it around. So another way to see this without the radical is if I cube root both sides. So I'll cube root this side and cube root that side, but I won't have a radical. It'll just be x squared plus y squared. We've gotten rid of the parentheses equals x to the 2/3 power, like that. And in a more general form, with everything moved to the left, you'll get x squared plus y squared minus x to the 2/3 equals 0. So that deserves a real, maybe virtual handshake there for doing all that work and getting into a nice looking rectangular form. Are you wondering what this graph looks like? Because I was thinking you might be wondering, and I want to type this into Desmos and see what it looks like. Almost looks like a circle, but not with this x to the 2/3 term sneaking in there. Maybe part of it will have to do with the circle. So our equation was x squared plus y squared minus x, what was it, to the 2/3 power? X to the 2/3, wait for it, equals 0. Check it out. It's like I've got eyeballs here. So you've got these two kind of circular looking shapes. They come out a half a unit each way, right? But they're not completely circular, and they are based off of, this is why this is called polar graphing. They're both connected to the pole, which is the origin. So crazy looking graph, and thankfully we're able to convert it and then be able to see what it looks like. Okay, one more. Number 4. R squared equals sine of 2 theta. I could think of 2 really cool strategies for this one. I'm going to at least offer one of them to you. And if you come up with some other way that works for you to convert this, by all means, give it a try. You might even want to pause the video and try to convert this on your own first. A big hint is look at this 2 theta staring you in the face. It wants you to use a double angle identity. So that's what I'm going to try here. Let's write it as r squared equals. We only have one version of this double angle identity. It was 2 sine of theta cosine of theta. You're just way better off if you have this thing in terms of just sine and cosine of theta instead of, I'll put ID for identity, instead of sine of 2 theta or cosine of 2 theta. So a good use of a double angle identity here. Now we got to convert, and I'm going to just try to do this left to right. This is one way to tackle it. So not introducing any more r's, which you could. You could actually multiply both sides by r squared, and that would be a good way to do this one. But instead, let me try to just work with what I have. For r squared, I can plug in x squared plus y squared. That's a nice substitution on the left. On the right, I don't exactly have what I need, but I can start to convert this. So I don't have r sine theta and I don't have r cos theta because I didn't make that happen. But I do know the definition of sine and the definition of cosine, and that can get me halfway there. Instead of writing sine, I know that sine of theta by definition equals y over r, and cosine of theta by definition equals x over r. These are the substitutions I'm going to use. I'll still have r's left in my answer, but we'll handle that in a second step. So it'll be y over r and x over r. So we're almost there. We're almost to complete rectangular form. X squared plus y squared. Let me just write this as a one fraction, 2xy over r squared. R squared doesn't square me. It doesn't scare me. That was a bad joke because I know I can do a sub in now in terms of x and y. X squared plus y squared equals, speaking of x squared plus y squared, that's what r squared equals. So I can write another one of these down here. So now you get the slight pat on the back for getting it converted to rectangular form. Pretty good, pretty good. We could get rid of this fraction, just make this a squared power, right? It would be x squared multiplying both sides by what's in that denominator. X squared plus y squared equals 2xy, like that. You can definitely leave your answer like this. There is absolutely no problem with that. What's tricky sometimes about these and frustrating, it's like you could get midway through the problem, and as soon as you've converted, like maybe back at this step here, I might be thinking, is that enough? Can I leave it this way? The good news is you can leave this one in either form. Now I'm wondering before we go, anybody wondering what this graph looks like? And you've got to be wondering. Let's take a look at it. So we'll try to graph this one for the road. So there was an x squared plus y squared squared. There are a lot of squares in this one. Okay, moment, big reveal, equals 2x, wait for it, y? Yikes! Okay, spoiler alert, this is called a lemniscate. Kind of sounds like a biscuit, but it's like a little bow tie on its side, or an infinity symbol, and we just successfully converted its equation from polar to rectangular form. Okay, one last virtual high five. Enjoy the rest of your day. See you later!